Hello friends, I welcome you in lecture number 4 on sampling distributions. In earlier lectures, we have discussed about sampling distribution of the sample mean when sigma was known to us. That is, we know that if we consider a sample of size n from a population with mean mu and standard deviation sigma, and if we have this sample which is having sample size greater than or equal to 30, then we know that z equal to x bar minus population mean divided by population standard deviation over square root of n. This becomes a standard normal random variable, and using this standard normal random variable we can discuss the probability statements related to the sample mean, which we consider as a random variable. So sampling distribution of the sample mean when sigma is known is given by this random variable z, which is a standard normal random variable. So this is valid if sample size is large, that is n is 30 or more. If sample size is 30 or more, then we can say that this sample mean is normally distributed. Also, we have discussed that if underlying population is normal, then regardless of the sample size, this becomes a standard normal random variable. If sample size is 30 or more, then we don't require the assumption that underlying population is normal, and if sample size is small, then under the assumption that original population is having normal distribution, we can use this random variable z. Now sometimes suppose we don't know the value of sigma, that is population standard deviation. Suppose sigma is unknown, then we can replace this population standard deviation by sample standard deviation, which we denote by capital S. But if sample size is large, then this is going to be valid if we replace sigma by sample standard deviation. But suppose we have smaller samples, that is sample size is less than 30, and if we consider z equal to x bar minus mu divided by s over square root of n, then this is no longer valid. We cannot say that we cannot use this random variable z, or we cannot use the standard normal probability distribution for the sampling distribution of sample mean x bar. So sampling distribution of the sample mean x bar when sigma is unknown is not a standard normal distribution. So what is the solution for this type of problem? That is, if the population standard deviation is unknown and sample size is small, then how to decide the sampling distribution of the sample mean? So the solution is we have new distribution which is known as t distribution. So we consider this random variable equal to t. We define t equal to x bar minus mu divided by s over square root of n, where this s is a sample standard deviation. Now if we recall, we have the definition of sample variance as sigma x minus sample mean whole square divided by n minus 1, and sample standard deviation is square root of this quantity. So we can see this sample variance depends on this n minus 1. For samples of different size n, we will have different sample variances and different sample standard deviations. So here, because we are using sample standard deviation instead of population standard deviation, this quantity is always constant, but this quantity is not fixed, it is a variable quantity. So error is going to be larger as compared to using this population standard deviation. So this will depend on the size of the sample, or we can say that it will depend on this parameter which is known as degrees of freedom, and it is denoted by nu. This nu is given by n minus 1, and it is parameter of this nu distribution known as t distribution. So for different degrees of freedom we will have different values of t, or accordingly for different values of n, or for samples of different size we will have different shapes of the t distribution. So t distribution depends on the degrees of freedom given by nu equal to n minus 1, and we will use t distribution whenever we have a small sample and we are using this sample standard deviation in this formula instead of population standard deviation, or we can say that we are just replacing this sigma which is unknown by sample standard deviation s. So if we replace this sigma by s, then we will have t distribution which depends on the sample size or on the degrees of freedom. Now the t distribution is having a shape which is bell shaped as per the normal distribution. The shape of t distribution is also bell shaped and it is symmetric curve as in the case of normal distribution, and the mean of this t random variable is also 0 as in the case of standard normal random variable. But we know that variance of standard normal random variable is 1, but that is not the case in the case of t distribution. Variance of t distribution is not 1, but mean of t distribution is always 0. So, and it is a symmetric distribution. Another difference between standard normal and t distribution is graph of t distribution will have heavier tails as compared to normal distribution. Suppose we have suppose this is the graph of normal distribution, then graph of t distribution for smaller samples will be having heavier tails. For example, this is the graph of t distribution for some sample of size say n equal to 3, then nu will be degrees of freedom, that is 2. So for 2 degrees of freedom, suppose this is the shape of t distribution, so we can see this t distribution has heavier tails as compared to this normal distribution. So t distribution is having heavier tails as compared to normal distribution, but if we increase the degrees of freedom, then it will approach normal distribution. Suppose I increase the degrees of freedom, then I will get this type of shapes. For degrees of freedom greater than 3, I will obtain this green curve. Similarly, if I keep on increasing the degrees of freedom, then as n will increase, that is degrees of freedom will increase, and if we take degrees of freedom tending to infinity, then this t distribution will approach standard normal distribution. So for higher degrees of freedom, t distribution resembles standard normal distribution. So here I have written all these things systematically. Sampling distribution of the sample mean when sigma is unknown. So we are going to use this theorem. If x bar is the mean of a random sample of size n taken from a normal population, to use this t random variable we use that underlying population is normal, having the mean mu and variance s square denoted by s square, then t equal to x bar minus mu divided by s over square root of n is a random variable having the t distribution with parameter nu equal to n minus 1. The parameter nu Okay, we read this as nu, nu. The parameter nu is called degrees of freedom. It is given by sample size -1. As I discussed, the overall shape of a t distribution is similar to that of a normal distribution, that is, both are bell shaped and symmetrical about the mean. Like the standard normal distribution, the t distribution has mean 0, but its variance depends on the parameter nu, which is equal to n-1, the number of degrees of freedom. Okay, because we know this formula, sample variance is given by sigma x minus x bar whole square divided by n-1. T distribution has heavier tails than the standard normal distribution. So as I discussed, okay, let me sketch again. Suppose this is the graph of standard normal distribution, then graph of t distribution for some degrees of freedom may look like this. So you can compare the tails of this graph are heavier as compared to the tails of this standard normal graph. But as we increase the sample size, degrees of freedom will increase, and as I discussed, we will have this type of t distributions which will approach the standard normal distribution. For example, I can have this type of shape if I increase the degrees of freedom. Here I have shown for two graphs. This graph in black color is the graph of standard normal distribution, and this green color is the graph of t distribution with 2 degrees of freedom. So you can see it is having heavier tails as compared to the graph of standard normal distribution. Similarly, this is the graph of t distribution with 5 degrees of freedom, and we can see for 2 degrees of freedom we are having heavier tails as compared to the t distribution with 5 degrees of freedom. So as we increase the degrees of freedom, or as we increase the sample size, this t distribution is approximating a standard normal distribution. So that I have written here, as the sample size n increases, t distribution closely resembles the standard normal distribution. T distribution with new degrees of freedom approaches the standard normal distribution as nu tending to infinity. Nu is n-1, so we can say that as n tending to infinity. So this is all about t distribution. We just have to remember this formula for random variable which defines a t distribution. T equal to x bar minus mu divided by sample standard deviation over square root of n, and we will use t distribution if we don't know the sample population standard deviation, that is sigma is unknown, then sampling distribution of the sample mean is t distribution, and if sigma is known, then sampling distribution of the sample mean is standard normal distribution given by z equal to x bar minus mu over sigma over square root of n. So here sigma is known to us. If sigma is unknown, then we can replace this sigma by sample standard deviation, and that will become a t distribution. And for samples having large size, t distribution is tending toward the standard normal distribution. Now, as in the case of standard normal probability tables, we are having t table for t distribution. So for that, suppose I consider this graph of t distribution for some degrees of freedom, and suppose I assume that the area to the right side of this line, say this area is alpha, and we know that t distribution has mean 0, so this is 0, and the graph of t distribution is bell shaped curve, or it is symmetrical about mean of t distribution, which is 0. So we are interested in the value of t denoted by t alpha such that area to the right side of this line is alpha. In other words, we can say that we are interested in that value of t for which probability that t is bigger than t alpha will be equal to alpha. This probability is nothing but value of this area, and that is alpha. So here alpha is known as level of significance. We will discuss in detail about the level of significance in upcoming lectures, but here we assume that alpha is called level of significance, and this t alpha is the value of t known as critical value of t. So we are having a table for critical values of t alpha. We are having values of t alpha such that the area to the right side of t alpha is alpha. So for that we require two things to find out critical values of t. We require degrees of freedom, that is n-1, and we require alpha, that is level of significance. So I will show you how to use t distribution table. So here is the values of t alpha. We can say that this is the table for values of t alpha or critical values of t alpha. So values in the table are critical values of t alpha. All these values are values of t alpha such that probability that t is greater than t alpha is equal to alpha. And in this column we are given degrees of freedom nu, which is equal to n-1, and in this row we have different levels of significance, that is we have different values of alpha. Here alpha is 0.1, 0.05, 0.025 and so on. So we will require that what is the value of t alpha such that area to the right side of t alpha is equal to alpha. So this is the area, this shaded area is this probability, and that area is equal to alpha. So we will require critical values of t, that is we will require that value of t alpha such that area to the right side of t alpha is alpha, and that we will require for given degrees of freedom and given level of significance. So we will require that what will be the value of t alpha for, suppose we assume that sample size is say 10, then we can say that nu, that is degrees of freedom, will be equal to 10-1, that is 9, and suppose we want to decide critical value of t for 0.01 level of significance. So we will search for nu equal to 9 and alpha equal to 0.01 in this table. So alpha is 0.01 means we have to search under this alpha, and nu equal to 9. So under these values of nu we have 9 here, and here we have alpha equal to 0.01. So we consider these two lines and we find out the value of t at the intersection. So you can observe that this is the point of intersection. So this is the value of t or value of t alpha corresponding to 9 degrees of freedom and 0.01 level of significance. So we can say that probability that t is greater than 2.821 will be equal to alpha, that is 0.01. So this is the value of t at level 0.01. So some authors are denoting this value by t sub 0.01 also. This we can denote by t suffix 0.01. So in this way we can obtain critical values of t for given degrees of freedom and for given level of significance. We will discuss about level of significance in detail in upcoming lectures. The purpose of this lecture was to introduce about t distribution, and we have seen that it is given by t equal to x bar minus mu divided by sample standard deviation over square root of n, and this we will use when sigma is unknown and we have small samples. So this is all about this session. I hope you like it.